Hi guys, so let's talk about sound again. So sound is a longitudinal wave, which means that the disturbance is parallel to the direction of propagation. So each time you have a wave, something has to shake. So for a sound wave, when you have a wave, it's the particles here, the particles or waves that are shaking. So each time you have a sound wave, you're going to have compression here. So high pressure, low pressure, high pressure, low pressure, high pressure, and it's moving along at the speed of sound. So again, let's look at that great simulation. You see that air is made of molecules. You have nitrogen, oxygen, 20% oxygen, 80% nitrogen, some CO2 and CO2 and so forth and so on, but mostly nitrogen and oxygen. And you see these molecules are already moving in a random motion. That's because of the temperature. If you increase the temperature, they're going to shake faster, but again, in a random motion. So they do have kinetic energy. Now I'm going to have that speaker produce a sound. So it's going to start to vibrate at a given frequency. So back and forth, okay? And you're gonna have a sound wave here moving along at a given frequency. And you can have, if you are, you can have a model here, you can have your, let's see, if I make a graph here, you can see the sine wave. So the top here will be high pressure, and the throw here will be low pressure. And you see how it's moving along. You can see that as wavefront. Okay, so you have area of high pressure, low pressure, high pressure, low pressure. And if you are far away, far enough, all those wavefronts will be parallel to each other. So we already talked about that. I can increase the frequency here. And you see I decrease the wavelength. Okay, so let's look at my slides. So those slides come from, again, Johnson and Cutnell physics. So it's great if you are taking the MCAT. So you see you have a speaker. So usually, so that will be the case if you make a sound in a tube. You can even make a standing wave if you are playing music. But if you have a speaker here, you see how it's going to spread out in space. As you move away from the source, you see here the energy spread out over a larger area if it's in 3 dimensions, right? So larger area, meaning the energy per unit area will get smaller. So the amplitude gets smaller. So that's why here, if you look at that simulation again, and I will put the link in the description, you see how the amplitude gets smaller because the energy gets spread over a larger area. Okay? Okay, I have another simulation to show you. It's great simulation. See? Now you can see this thing is vibrating back and forth at a given frequency. So again, the frequency is the number of cycles per second. So the one cycle, you start from here, you go back, and then you go forward again. That will be one cycle. So very low frequency. You see these little particles here in red, they are not going along with the wave. They are staying and they just vibrate or oscillate about their equilibrium position. So it's a simple harmonic motion. So you see you have area of high pressure. High pressure meaning above the atmospheric pressure. And you have area of low pressure. So it means lower the atmospheric pressure. And it's moving along. So I could find, how long it takes for that front here to get to here. Okay. Measure the distance, you divide by the time, and you have the speed of the wave. And then if I increase the frequency, you see I have a smaller wavelength. Okay. Because the speed is given in about room temperature, it's about 343 meters per second. We talk about that. So if you increase the frequency, the wavelength decreases. So if I don't know if I can pause, but again, you can see here, we talked about that before. So here you have high pressure, low pressure, relative to the atmospheric pressure, right? No, my tablet doesn't work. So that distance here, that will be the wavelength. Okay, so you can go from high pressure to high pressure, low pressure to low pressure. That will be the wavelength. So this is rarefaction, and that's compression. So from here to there, that's going to be half of the wavelength. Okay. So of course, in reality, it's not like just in a straight line. It's going to be more, let's see if I have here. So the sound can be produced in 3 dimensions. So when you talk, for example, the sound will go in 3 dimensions, right? So it doesn't make a sphere, but at least it's making half of the sphere. See, and it's moving along. So let's go back to the slide. So the frequency, of course, we already have defined those physical quantities. Frequency, okay, so the number of cycles per second. These slides are very old. That's because I'm old. You see, it's an old phone from my time. A sound with a single frequency is called a pure tone. So that will be, for example, a tuning fork. Okay, tuning fork will have like one pitch, and it will use its first mode essentially. The pitch is what we interpret as the frequency, right? So we talk about the physics of music already, so I'm not going to go back and talk about that. So you see here, when you make a sound, you can attach here a gauge, like a pressure gauge. So the same type of gauge you attach to your tire to verify the pressure. So it's not the absolute pressure, but it's relative to the atmospheric pressure. So this is low pressure, high pressure, low pressure, high pressure. And you use a sine wave here, right? So amplitude is large, that means high pressure. Then the amplitude here is negative. It means with sine wave, that means low pressure. Okay. So the loudness of a sound depends on the amplitude of the wave, right? So if you have a high amplitude, so that means high pressure or low pressure relative to the atmospheric pressure, that means that the sound will be louder compared to a sound with a smaller amplitude. So for example, here, if you have I found this picture very cute here. So you see the sound is not very loud, and you see you're not going to go very much above or below the atmospheric pressure. So you have a small amplitude. If the sound is very loud, so the pressure will be large relative to the atmospheric pressure. Okay, so the amplitude, will define the loudness. So the amplitude also depends on how much energy is being carried along the wave, right? So more energy louder is the wave. The relationship is as follow, but we're going to see that next. So the amount of energy per unit area. So for example, the amount of energy here going through this area here per unit second and per unit area will be equals to the amplitude square. So louder is the sound, more energy is being carried. And if you have more energy carried, when it gets to your eardrum here, it means it will push and pull the eardrum with a larger force. The force applied will be larger. So of course, we're going to perceive that in our brain like a stronger sound, larger sound. So sound can only move if you have medium, right? So if you have a gas or a liquid or a solid. So for example, here I have molecules here. They're already moving, okay? Because they have a random motion because of the temperature. So then I can push and pull on them, okay? So I can make a sound wave. So now if those molecules are closer to each other, like in a liquid, so it will be easier for those molecules to pass on the disturbance. So the sound will move faster. So the sound will move about at a speed of 1500 meters per second in water and only 340 meters per second in gas. If you have solid, so all those molecules are going to be connected to each other, so it's going to be even easier to have a pressure wave. In addition to that, if you have a gas, the speed of sound depends on the temperature because you see those particles, they have a random motion. So if you increase the temperature, this motion is going to increase. They're going to move faster. If they move faster, that means the sound will be passed on faster, right? So actually the speed of sound will be the speed of those little molecules jingling around. So if you go back to the slide here, you see in gases, you can have the speed of sound, room temperature will be about 343. Okay. The speed of sound will be larger in helium, okay, because helium has less inertia than air molecules. So that's why if you inhale helium, for example, the air molecules will be able to move faster, okay, because they have less inertia, less mass. And that's why you're going to talk like this, right? Because they're going to move faster, so you're going to have a higher frequency than expected. So in a liquid, you see that also, you're going to also have a larger speed and solid even larger. So there is all physics about that. You know, it's not that interesting. You can find the relationship here to find the speed of sound in liquid here or in solid. So it depends on the inertia. So larger inertia, smaller speed. Makes sense. It's harder to move the molecules, right? To move the sound along. And it depends on the restoring force. So for liquid, it depends on the bulk modulus. And for solid here, we have here the Young's modulus. So it's very much like the spring has the K, the spring constant, right? So it relates to the restoring force, how fast those molecules will spring back to their initial position. Okay, so just a relationship. For gas, you can work with the gas law, the ideal gas law. You can do the math, and you get to that equation, for example, for air, and you see how it depends on the temperature here. Okay, so if you increase the temperature, the sound will move faster. So here we talked about that. It's nice to remember that the sound approximately in air will move 1 mile in 5 seconds. So if you see lightning, for example, it's almost instantaneous because the speed of light is so big. It's 3 times 10 to the 8 meter per second. So you see lightning right away, and then you hear the sound lagging behind. So if you count 5 seconds between lightning that you see and the sound of thunder, that means it's 1 mile away. If you count 10 seconds, it's 2 miles away. Otherwise, if you cannot count even 1 second, it means it's just above your head, right? And maybe you have to look for cover. So now, just to go back to the beginning of the slides here, we talk how all waves have those properties here. So here I have light, but that's going to be true for waves, sound waves or water waves. So wave can be refracted. So that happens when they go from one medium to another one with different properties. So if you go from, for example, with seismic waves, for example, if you go from water to ground, or if you go from the mantle to the outer core, for example, the seismic waves that are P waves, for example, are pressure waves like sound. You see how they can be refracted, okay? So they can bend here. So there is a bending here because the medium is changing property. The density is changing. They can be reflected. So we already saw that with sound. We talked about reflection, echolocation, and waves can be diffracted. So this is refraction, this is diffracted. Diffraction happens when wave bend. There is a corner here, it bends around the corner. Okay? So you can have that with light and you can have that with sound. So that's what we're going to talk about. Not going into details, but just so you see here, if I go back to the last lecture, you see those P waves. They are like pressure wave, right? Like sound. So they can be reflected and they can be refracted when they go from one medium to another one. So let's go back to sound here. So you might expect like someone is talking in this room and you have a door. That sound will just go in a straight line, but that's not what's happening. You have something called diffraction. So it means sound will bend around the corner and it's going to spread out like a fan. So how much spread happens depends on the wavelength and the size of the opening. So you can think of a wavelength like the size of the wave, right? So the wavelength is the size of the wave. So if the wavelength is small relative to the opening here, so if you have a wavelength smaller than the opening, so it means that the wavelength, the wave, because it's small, it doesn't feel the opening because it's smaller than the opening. So it will tend to do this. But if the wavelength is larger than the opening, okay, so it means when it's going through, it's like feeling the opening. It says, okay, there is an opening here, so I'm going to bend around, okay? So that's why even if you are standing here, you can hear the person. Otherwise, it will not be the case, right? So if sound will behave this way, you will not hear the person if you are standing there. Okay? So it depends on two things. It depends on the size of the opening and the size of the wave. So I'm going to show you a simulation, but that's the idea, and it's called diffraction, right? So there is a wave. If the wave has a wavelength smaller than the opening, then it will fill the corner here and it can spread around. So it's a special case of interference, but here I have a nice simulation somewhere, wave interference. So diffraction is a special case of interference, but I just want to show you the So for example, here you have a sound generator and you have an opening here. So you have a sound wave going through the opening, and you see how it's spreading out. Okay. Now, if I decrease the size of the opening, if I decrease the size of the opening, so now you see it's going to spread out even more, and the amplitude is going to decrease as well because the energy is spread out over a larger place here. If I increase the opening here, so I'm increasing the opening, so now it doesn't spread that much, okay, and then it keeps the amplitude high. So you have some stuff here, but not that much. You see, most of the sound will come here almost straight through. I can also play with the frequency. So if you increase the frequency, so you get this here. So if you increase the frequency, you're gonna decrease the wavelength, so it doesn't spread that much. So you increase the frequency, so you see the wavelength is gonna decrease, and you don't have that much diffraction. So you see, I keep the amplitude very large here in that neighborhood, and it doesn't spread that much. I can do the same thing with light, of course. Can have green light here. So green light, if it has a small opening, so an opening which is smaller than the wavelength of green light, so it's going to spread out. I can even have a screen, and you see by how much it's spreading out. So you compare this size here to the size of the opening. You see, you can almost make a line from here to there, a line from here to there. So you have a triangle, and you can find the sign here, the angle by how much it's spreading out. Now, if I decrease, if I open, make a bigger opening, you see this size here will be about the size of the opening. So it does not spread out that much. You can decrease the opening here, and now that size here is much bigger than that one. And it's so big that you cannot, it's spread out so much here that you cannot even see the color. So I recommend that you play with this simulation. You can change the frequency. So if you have a larger frequency, for example, if you have red, it's going to spread out even more. So red, you see, this is much bigger than the size here. You can decrease, you can increase the opening. So this size here will be about that one. Okay, so anyways, this is called diffraction. So you have diffraction with sound, and you have this equation here by how much it's going to spread out. You see here you have all that area here over which most of the wave will spread out, and you have this equation here. So the sine, so that will be the angle here. It depends on the wavelength and the size of the opening. So if you have a small wavelength, okay, the size smaller than the opening, it's not going to fill the opening, and it's not going to spread out that much. Or you can have a very large opening relative to the wavelength. So the wavelength does not fill the opening, it doesn't spread out. Okay? So that's interesting for sound because, for example, if you have like high frequency, so high frequency, high pitch, small wavelength, it's not going to spread out as much as low frequency. So low frequency have large wavelength. So you can think of a speaker like an opening, right? It's like an opening. So loud sound will spread out more. Okay. So it means at that distance here, the amplitude of the low frequency will be smaller than the amplitude of the high frequency, because here the energy has to spread out a lot relative to this. So here you will have a small amplitude, okay? So it's going to be harder to hear the sound, and you're going to hear the high pitch more easily. So usually you have two sides on the speaker. You're going to have the woofer and the tweeter. So that will be for high frequency and for low frequency. With this large speaker, it's going to push and pull more air. So it's going to amplify the amplitude of the low frequency. So even though you have diffraction, you will be able to hear it at a large distance. And for the high frequency, you need a small speaker or small cone, because the frequency is so large that you need to have a small inertia, right, to react, to bounce very, very fast. Otherwise, you will have a mismatch of impedance. So you need a small speaker for the high frequency, so you will be able to push and pull, and you need a large speaker for the low frequency to make sure that you can push and pull enough air to have enough pressure to make enough amplitude so you can hear the sound. So this is because of diffraction. So when you go to light, of course, diffraction is going to be a big deal if you are using telescope, because light is a wave, and a telescope is an opening. So when light from stars are coming through your telescope, light will be diffracting. And what can happen is that, like if you are looking at two stars here, but in the red has a large wavelength. So you see how those two points are merging together. But if you are looking in the blue has a small wavelength, so you can tell them apart. That because red light tend to diffract more. Okay, so you see you have the same kind of equation here. The wavelength divided by the opening. Okay, picture for diffraction. So let me show you even more applications here. So again, that's diffraction. You see light going through an opening will spread out, okay? And how much spreading out happens depends on the wavelength. So if the wavelength is smaller than the opening, then the spread out will be small. But if the wavelength is about the same size of the opening or larger than the opening, so it's spread out more. Lots of applications, for example, radio waves. If you have FM have a small wavelength relative to the size of mountains or building. So, for example, if you are standing here, you are not able to catch the broadcast because this is a corner, so it doesn't spread out. Okay? If you have AM, have a large wavelength, so it's going to fill the corner here, so it's going to spread out. So if you are listening to AM radio, for example, you see those waves here have a large waveband, so they're going to fill the corner and it's going to spread out, so you will be able to hear the broadcast. If it's FM, you're not going to be able to hear it. It works also with water wave. So you have water coming here and you have an obstacle here. You're still going to have some wave here because the wave here, if they have a wavelength, about the same size as this obstacle here, they're gonna spread out around the corner, okay? So you still have diffraction. I have another image here. See, this is water wave here. The opening is small, so you can have a lot of spreading out. The opening is large relative to the wavelength, so it doesn't spread out that much. So this is super interesting. So diffraction here, I have another picture. See how it's spreading out. That happens only if the wavelength here is about the same size as the opening or even larger. And you can find that angle here. That angle here is about the wavelength, the wavelength of the wave divided by the opening. So interestingly, this is why if you are lost at sea, for example, you're gonna use a horn, right? A fog horn, a fog horn, something like this. You can use also to scare animal, right? It's called a fog horn. So it has a very low frequency. So low frequency means large wavelength. So let's say you are lost here at sea and no one can hear you because maybe there is some obstacle in front, maybe there is a rock here, maybe there is an iceberg, and you want to be heard, right? Maybe there is another ship here that can come to your help. If you have those huge fog horns here, the wave is not going to be stopped by that because the wavelength of the wave is so large that it's going to spread around and you can be heard by someone over there, right? So fog horns, it's good. If you do hiking, it's very important to have to scare bear away. Okay, so this is what a fog horn looks like. So it's going to produce very low frequency with large wavelength. So if there is like something on the way between you and help, the fog horn will be able to go around the obstacle, right? So that's called diffraction. Now you have also something called refraction. So that was diffraction. So it's spread around here. Now you have refraction. That happens when there is a change in the speed of the wave. So for sound will move faster in warm air and slower in cool air. Right? Because warm air, the air molecules will move faster. Cool air, the air molecule move slower. So that will be slow speed, high speed. So let's say it's in the morning. So in the morning, this is cool here because the sun didn't have time to warm up the ground, and this is warmer. So you're going to be able to hear the sound from very far away because instead of going in a straight line, the sound will curve down. So if you live next to a train station, you will be able to hear the train. It's going to wake you up. In the evening is the opposite. The ground is still very warm. Here it's going to be cool. So the sound will, bend away. So you're not going to hear it at a large distance. So likewise, you can also explain the mirage. Then I have a picture of a mirage here. If you have a mirage here, it's so the light. So this is light will move faster in warm air and slower in cool air. Okay, so what's going to happen here? If the ground is very hot, the light coming from a tree here. Maybe there is a tree, there is some ground here. The light will curve away from the ground, and you're gonna see a virtual image here. So from your point of view, from the point of view of your brain, light comes from this direction. So you're gonna see a virtual image, and you're gonna think that maybe you're gonna have water here, and you're gonna be disappointed. So this is called diffraction. So works the same way. You see, same way, because this is warm, this is cool, and it's going this way. And for a mirage, for light, it works also the same way. This is warm, this is cool, and it's going this way. And you see your mirage here. So you can look up refraction. You can explain that, for example, imagine that you have a train here coming, and there is a change in medium. So maybe you have grass or mud. So it's coming in a straight line, and here, this size here will be forced to slow down, so it's going to burn in this direction. If this is the opposite, so if it's going from low speed to high speed, it's going to burn in the opposite direction. Okay? So refraction also for sound. So then you have what is called interference. You have constructive interference and destructive interference. So what's happening is it works also for any wave, because a wave can be at the same place and at the same time, and the same place. So if you have two crests at the same place at the same time, the crests are going to add up, and you have a constructive interference, and the sound will be very loud. So that works if you have the same frequency, so the same wavelength, right? So you have two speakers here, and they have, of course, the same frequency. So you can have spot where it's going to be very loud, and you can have spots where you're not going to hear anything. So they call that blind spot, because you have a crest, high pressure, and a throat, low pressure. So at that spot here, there is no wave. It's going to be flat. So it's called interference. So let me show you. I think I have a simulation here. So you have two waves. Let's move it to see. Okay, so you have two speakers. One is blue here and one is red. And when you add them up, you get that pink wave here. So if the speakers are, of course, at the same distance from you, they're going to interfere. The two sound from the two speakers interfere with each other, and it's going to be very loud. If you are at a distance half the wavelength, so just half of the wavelength, so distance between here and there is half of the wavelength, so you see you're going to have a crest and a throat, and you're not going to hear anything. Okay? I have a great video to show you. I will put the reference in the description. It's a website. It's not a website. It's a YouTube channel called Veritasium. Veritas means truth, so Veritasium. And it has a great demo. So I will put the link in the description. So I'm going to skip through to show you interference. So he has two sources of waves, right? So it's going to check them exactly at the same frequency. So you have two sources, same frequency. So the waves, they're going to interfere with each other because they can be at the same place and at the same time.
Of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But
it's a beautiful demo. Can you see the wavelength here? And can you see that here the amplitude is very large, and as you move away from the source, the amplitude is going to decrease, right? That's because the same amount of energy that you have here is going to spread out over a larger distance here. It's circular. So that's why the amplitude will be smaller, because the same energy that you had to begin with is going to spread out more.
if I add a second source of ripples, then we start getting an interesting pattern.
Here.
This pattern is created by the ripples from the two sources interacting with each other. Where they meet up, peaks with peaks and troughs with troughs.
Okay, isn't that amazing? Look at that. Here, along those lines, you have crest from this one meeting a throw from that one, and you get something flat. When crest and throw are superimposed to each other, you're going to have a high amplitude here, high pressure or low pressure.
The amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there.
Okay, so you can do the same thing with light. So I think it's a very nice video. And let me show you a simulation now. Let's see, where is my simulation? Wave interference. Okay, so you have a sound here. You have two opening here. So it's like you have two sources and it's the same frequency. So in this area, the wave are going to interfere with each other. And in those here, along here, and along there, there won't be any sound. And you can see that here. So this here, I have high pressure, low pressure. Okay, so crest to crest, throw to throw. But if I put this one here, you see, no sound. Okay, no difference in pressure. So there is no sound here, no sound here, high sound, high sound, high sound, no sound, no sound. Okay, so if I compare the amplitude here with the amplitude there, of course here it's going to be larger because here it's going to spread out. You also have diffraction. And if you put here, no sound. What is nice here, you can see the same thing with light. So you see light, you have two sources of light with the same frequency, and you can have here, there is no light. You can put a screen here, no light here, no light, bright spot. You still have diffraction here, you see it spreading around, and then you have bands, bright, dark, bright, dark, bright. Isn't that cool? So here, no light, and here, very bright light. So you can play with that. You can do the same thing with water. Okay, you can make water wave, and you're gonna have no wave. It's gonna be flat here, high wave, high wave. So let's go back to the slides. So that means that if they are crest to crest, it's going to be constructive. Crest to throw, it's going to be destructive. So if the distance between those, the distance between the listener and the speaker, the difference between those distance here is exactly half of a wavelength, okay? Or 3 half of the wavelength, or 4 half of the wavelength, then it's going to be destructive. If it's 1 wavelength, 2 wavelength, 3 wavelength, it's going to be constructive. So that's going to be constructive. Sorry, here it's going to be constructive. They are exactly in phase. So a crest will match with a crest, a throw will match with a throw, and we get twice the amplitude. If they are out of phase, okay, so a crest here will match a throw, and you get destructive interference. So that's how it works. Okay, I have these nice pictures that I have made, and you see crest to crest, it's going to be very loud. Crest to throw, it's going to be nothing. It's going to be a blind spot. And you see that if you are listening to music in a home which is not does not have a good acoustic, you're going to sit at some place, you're not going to hear anything, and at some place it's going to be very loud. So you have to be very careful when you do the connections with speakers. You don't want to have speakers out of phase, otherwise you're not going to hear anything. Okay, so let's take an example. So if they are in phase, okay, so the distance, the difference between the distance here, that distance here minus this distance here, will be equals to 1 wavelength, 2 times the wavelength, 3 times the wavelength, and so forth and so on. But if they are half the wavelength, 1.5 the wavelength, 2.5 the wavelength, they destroy each other out. Okay, so let's do some. Okay, I just changed. Didn't have enough space, so I changed the app. So you have one speaker here. So you have a sound wave. Let's do up, and then let's do down and up. And here, let's see, I'm located here. Okay, and then there is another speaker. That other speaker is at 7.2 meters, and you're not going to hear any sound. So that means the other speaker here, you're going to have a crest here. Okay. And here you're going to have a top. Okay. And then you have a crest here. Okay. And then you're going to have, you are out of phase. Okay, so the result of that is that you're not going to hear any sound if you are located here. So it's not a great drawing, but there is no sound. So they are shifted by half of a wavelength, okay? So this is half of a wave, shifted away by half of the wavelength. So if that distance here is 7.2, so this distance here is 7 meters. So that means they are out of phase, and it's the first distance, right? And then you can move, and it's going to be loud, and then move, that there will be no sound. So just shifted by 0.2 meters. So that's going to be half of a wavelength. So the wavelength is going to be 0.4 meters. So that means the frequency equals 343 divided by 0.4. What you get 857.5 hertz. So that's going to be the answer. And I don't know if you can, here you see, here the two speakers are the same distance. If I move one from the other one, just half of the wavelength, so now they are out of phase. So that means the crest from one will be matching with the throw of the other one. So what I get flat. So they destroy each other. And I can move away again. So now I am 2 wavelengths away. And again, it's going to be loud. So that I can start from here, right? So here they are at the same distance. Crest to crest, the sound is loud. And then just half of the wavelength, there is no sound. And then I have 2 wavelengths, there is a sound. And I can keep going. So I will put the link in the description and you can play with it. Okay, so let's do this one, number 2. So here there is no sound, right? No sound. So it means that 5.2 minus 4.7, it's going to be, I don't have my calculator, but what you're going to get here will be half of the wave. So you multiply by 2, right? So that's going to be 5. And it's going to be 0.5 meters. So that means the wavelength is going to be 1 meter, right? Okay, let's do another one. So this one, you can pause the video and try to do it. So you have 2 speakers, and the question is, and that comes, it's a slide from Johnson and Cutnell again. You have the distance here, D, and the question is, and they both have the same frequency, because you need to have the same frequency to have that destructive or constructive interference. And you want to know, will it be a loud sound or no sound? So first, let's find the wavelength. So the wavelength is the speed divided by the frequency, and you get 1.6 meters. Okay, so if the difference in the distance, so if that distance here from this distance here is 1 wavelength, so it's going to be loud. If it's 2 wavelength, it's going to be loud. If it's 3 wavelength, it's going to be loud. If it's half of a wavelength, then there will be no sound. 3 half, 5 half, 7 half, so forth and so on, no sound. So we need to find that distance here. So that distance here, you have to use Pythagorean theorem here. So it's going to be 3.2 square plus 2.4 square. And what you get 4 meters. Okay, so this is 4 meters. So it's the distance from this speaker, and you have the distance from that speaker here. So you're going to do 4 minus 2.4. And what you know, you get 1.6 meters, which is 1 wavelength. So you get loud sound. So it means the pressure add up. You can have twice twice the sound, right? So it means that twice the amplitude. So lots of applications for that. For example, you have canceling headphone. So if you don't want to hear noise from outside, so those headphones they have electronics inside, and so inside here you have a small microphone, and it's gonna pick up the noise coming from outside, okay, or the sound coming from outside, and using electronic, it's gonna make exactly the opposite wave, out of phase. It's gonna make the same wave, right? Even though it could be a random wave, just a waveform. It's going to take that waveform and make it one waveform just out of phase, so just the opposite. So it's going to cancel each other, and you're not going to hear anything, except that they are very expensive. But that's the idea, okay? So inside those headphones here, you have a microphone, you have electronics, and you have a small speaker. So it's very nice. So now the question is, what's going to happen if you have two waves, okay? So now the next question is, what's going to happen if you have not exactly the same frequency? So for example, if you sound two tuning fork, one is 440 Hertz, which is middle A, and the other one is 438 Hertz. So not exactly the same. So what you're gonna hear, you're gonna hear beats. That's how we can tune piano, for example, with the tuning fork. It will sound like right? So these are called beats. And you see you have two waves, still same place at the same time, but the period does not match, or the frequency does not match, right? So when they add up, you're going to get these types of waveform, okay? And the frequency of this new waveform will be the difference between the two frequencies. So let me show you. I have found a great video app here. I will put the link in the description. So these are two tuning forks. This one is 100 Hertz. This one is 100 Hertz. So of course I'm going to tap here, have a wave, and here I have another wave. And if you look closely, they're going to add up. Both of them will add up to the same wave, to the same frequency. So the sum will have the same frequency, 100 Hertz, except the amplitude will be twice as large. But now what's going to happen if I make this one a tiny bit maybe smaller, right? So maybe it's going to be 96 Hertz or 94 Hertz. And what I get is beats. And so that means in that case, so let's see, what do I get? So you see here, the frequency here is 100 Hertz. So the period is 0.01 seconds. The frequency for this one is 94 Hertz. Okay, so the period for that one is 94, the reciprocal of 94, which is about very close, 0.0106. Now, the waveform that you get here, you see the period? That's going to be the period between here and there. So we find the frequency of the beats. So these are called beats. by taking the difference between them. So it's going to be 100 minus 94, which is 6, right? 6 hertz, right? And then you take the reciprocal, and so the period of the beats is going to be 1/6, which is about 0.2. So between I don't know, here and there, so this is 0.1. Okay, so it's about 0.16. Okay, so 0.167 seconds. Okay, so that will be the period for the beats. So that's what happens when the frequencies are very close to each other. And then you can play, you know what's going to happen. I'm trying to play with that, but I recommend that you play with this to see what's going to happen if you change a lot the frequency or not that much. You can even look what's going on here. So it's a great simulation to play with. So there is a video here. Let's try. So this is a video by Paul Hewitt. Paul Hewitt, do you saw his name? He wrote a very good book. It's called Conceptual Physics, and it's a great book. And he did a lot of demo with the book.
Let me get these things so they're a little bit different in frequency. You strike them both at the same time. Can you hear the throbbing? That is the result of interference, and the phenomenon is called beats. All right.
Do you hear that?
Get these things so they're a little bit different in frequency. You strike them both at the same time. Can you hear the throbbing?
It's a very old video, but I like it. Okay, so let's see easy. So these problems, if you get them, they are very easy because you just need to know the definition. So a piano tuner adjusts a string. So you make a string sounds like a C264 hertz. So that's close to a middle C for piano. And the beats, he get 3 beats per second. So that means 3 beats per second. So what do we call beats? You know, is those things here. Okay, so 3 beats. 1, 2, 3. So that means the frequency is 3 hertz. Okay, so that means the frequency is 3 hertz. So that means it's either 267 hertz or it could be 261 hertz, right? 261 or 267. But if you look at the piano, the frequency, see, you have a lot of frequencies available for a piano. So middle A, 440 hertz, that's what they use for tuning 4. And then you have here, it's called the middle C. So you see here, it's around 261. There is no 267 here, so 261. So might be, probably, but it doesn't say, 261 hertz. Okay, so here it's the same thing. Beats of frequency of 3 hertz I heard. right? So same questions. So 3 hertz, that means 3 beats per second. So it could be 443 or 437. Okay. So 440 hertz is here. So you have 2 answers for this one. So piano is too high. So too high means the pitch is too high. So what should you do? So you have to loosen the wire, okay? Because remember the frequency when we look at standing waves, for a string, for example, is going to be depending on the speed, right? Depends on the speed. It's always depending on the speed. And the speed depends on the tension. So if the tension is high, the speed is high, so the frequency is high. So you need to lose it. Okay. So if you play 263 and 323, so the beat frequency will be the difference. So it will be 323 minus 263. So beats, for example, if you have that here and the beats, you can have 2 beats per second. That means that time will be 1 second. So this is 1 beat. That's what we call beats. Okay, so just a parenthesis here. We have studied standing waves in another series about simple harmonic motion. And I have introduced standing waves in terms of resonance. So we could talk about fundamental overtones and so forth and so on. But actually standing waves is the result of interference. So I can show you that. Let's see. I can show you that. I think there is one here. I can show you that here. Standing waves. So you see, when you have 2 waves, so one is going in this direction, and they both have the same frequency again. But now they are traveling, okay? So one is going in this direction, this one is going in that direction, and they have the same frequency. You see, you get standing waves. So standing waves can be explained by interference, and you can, like, even a wave on the rope. Let's go back to that. Let's see, I oscillation. I take a very small amplitude here, very small. And let's say maybe slow motion, no damping. I'm going to decrease the tension to make it slow. So I'm making a sine wave traveling. It's very slow. Maybe we're going to make it faster and slower. So now it's going to be reflected. You see how it's reflected? It's going to interact with the coming wave. And that's how you make standing waves. So one is moving in this direction. The other one is moving in the opposite direction. They interact with each other. And it's almost done. And that's how we make standing waves. So I can do that again. I will put also the link in the description so you can play with it. I'm going to slow down at the end. So damping. So it's coming. I'm going to be slow. Now it's going to be reflected. And then it's going to react. the reflected wave, okay, is going to interfere with the coming wave. So they're going to be at the same place at the same time. And the final result is a standing wave. You see, you have a node here, antinode, have a node here, antinode, node, antinode, node, antinode. Isn't that great? And okay, so that was another simulation, but you see standing waves here. So that's going to be the first harmonic. So you have a transverse wave here, like a rod, a wave on a string, and or you can have a sound wave. This is the second harmonics. This is the third harmonics. You see here, that's your node here, no pressure. And then here you have high pressure, low pressure. Now you can have open both sides. So that will be your flute. This is your node, antinode, antinode, second harmonic, third harmonics. Or you can have close. That will be a clarinet. So the first harmonic here, or the fundamental, that will define your pitch. So that will be a clarinet. Here you have the third one, because you don't have second, and then you have the fifth one. But we talk about that. It's just that it's a great simulation.